My name is Leah Gervin, and with John Brzezzi and Arjun Canaria, we are MEM Team 2. Our project was assembly process improvement through the implementation of a collaborative robot, also known as Cobot. We worked in conjunction with Mechanical Engineering Team 4, as well as our sponsors at Belimo, John Forlenzo and Tim Kaiser. Our sponsor Belimo is the global market leader in HVAC solutions, including custom valves, sensors, and actuators. Our team worked with the North American headquarters in Danbury, Connecticut. Our primary objectives were to identify a candidate subassembly, identify and recommend a cobot to purchase, as well as design a work cell and implementation plan for the selected subassembly process. Belimo's primary goals were to introduce automation to free up human capital for high-level processes, as well as lower costs while increasing production rates. Our first deliverable was to identify the candidate process for cobot implementation. After multiple site visits, our team worked with Belimo to identify and focus on 2 subassemblies which had the most potential for automation. The following 2 subassemblies were identified after researching the capabilities and operating standards of cobots, as well as considering other factors such as the number of manual steps, ergonomics, and production volume. By mapping the process flow for both subassembly A, a screwing operation, and for subassembly B, a shaft gear clip assembly, we came to the conclusion that Belimo would most benefit from automating subassembly B as it had higher non-value added time, as well as a higher cycle time. After the subassembly process had been selected, our team had to identify a cobot to recommend to Belimo. We began with the top cobots on the market, and then used several selection filters to narrow the list until our team had identified the top 3 cobot options. Using the weighted design matrix shown at the bottom of this slide, our team scored the remaining cobots to numerically determine the best cobot for Belimo. The factors considered were repeatability, durability, precision, ease of use, ease of programming, minimal useful life, and cost. Based on these considerations, our team recommended that Belimo purchase the Universal Robots UR5. Following our cobot recommendation, we designed the work cell in conjunction with the mechanical engineering group. Given that the workstation was to be placed on the factory floor, we were restricted to the 6-foot by 6-foot space shaded in green on the floor layout as to not interfere with the flow of other processes. Belimo will be custom designing this work cell from Bosch tubing based on the specifications from the CAD model shown. The shafts and gears will be racked in pallets of 25, and the C-clips will be loaded on a custom part feeder placed at the top of the workstation table. Shown here is a simulation of the cobot in action. The cobot will pick up a shaft from the pallet, place it into a die, pick up a gear from the pallet, and then use spiral switch to place it on top of the shaft. It will then pick up a C-clip, then press it onto the shaft, and then pick up the completed subassembly and place it into the empty pallet for finished parts. It will then repeat this process until 25 parts have been created. Once a shaft pallet is emptied, it is then stacked onto the full finished part pallets and used to store other completed subassemblies. Shown on this slide is the new process map compared to the unautomated process. While each batch individually takes longer, there is significantly less non-value added time. Furthermore, the cobot can run continuously for 200 parts, or 8 batches, without any human interaction, while a human worker would require breaks and cannot operate at such a consistent speed. Furthermore, human involvement is reduced by an average of 82% per batch, increasing productivity as that worker is now free to assist in other manufacturing processes. To justify Belimo's investment in the UR5, we created a model to gauge this project's financial impact. On the left, we have a break-even projection of the cumulative discounted cash flows, and we found that between years 2 and years 3, the cash inflows will surpass the cost. Furthermore, by year 10, we have a net present value, or NPV, of $75,000 and a return on investment, or ROI, of 6.6% for just the assembly process focused on in this presentation. To show the true value of the UR5 investment, we created an additional multi-project model. Based on the UR5's yearly utilization from our simulation, there are 362 days left in the year for the UR5 to operate. Assuming each additional project is of similar size and value to the shaft gear clip subassembly, we project a high impact to NPV and ROI. This is best demonstrated by our table in the bottom right-hand corner, which shows that 5 cobot applications will result in an NPV equal to $639,000 and no ROI of 11.7%. That concludes our team's presentation. We would like to thank John Forlenzo, Tim Kaiser, and Belimo for this learning opportunity, as well as Professors Jason Lee, Craig Calvert, and Francisco Cunha for their guidance throughout this project. Thank you.